Hello everyone, today we will discuss about the simplex method in solving some linear programs. The simplex method is very useful in many cases. So what is a linear program? A linear program is to maximize the function y, which is a scalar product between two n-dimensional real vectors c and x, where x satisfies the constraint a x less than or equal to b and x is non-negative. Here A is in m by n real matrix and b in m dimensional real vector. The domain X where Ax less than or equal to b and x is non-negative is called the feasible regions of the optimization problems, and the function y is called the objective function. For example, we aim to maximize the function y is equal to 4x1 plus 3x2, where x1 and x2 satisfy the constraints 4x1 plus 2x2 less than or equal to 8, x1 plus x2 less than or equal to 3. x1 and x2 are non-negative real numbers. By setting the vector x consisting of x1 and x2, the vector c consisting of 4 and 3, a 2x2 matrix A with entries 4, 2, 1, 1, and a vector b consisting of 8 and 3. We can transform this example into the general form of optimization problem that I introduced you before. Before we are going to explore the simplex method, we should transform the original optimization problem into its standard form by introducing some slack variable s. The slack variable is used to transform the inequality constraint Ix less than or equal to b into the equality constraint Ix plus s is equal to b. Here s in m-dimensional real vectors and e non-negative. In general, to deal with the standard form is much more easier than the general form of the optimization problem. One more thing, the objective function can also be considered as an equality constraint that I wrote in the red box. A very simple solution to this system of linear equations is that x is 0, y is 0, and s is the vector b. In this case, x equals the basic variables and x equals the non-basic variables. However, the solutions x is 0 and y is 0 is not the optimal solution that we need. So we need a method or an algorithm such that we can interchange the roles of the basic variable and the non-basic variable in order to increase the solution from 0 to the optimal solution. And that method is called the simplex method. And if it's possible, then Xj is equal the entering variables and Si is equal the leaving variable. Now we are going to explore deeper the simplex method by writing the system of linear equations into a tabular form, where the first row contains the variable names y, x, s, and the right-hand side of the linear equations. The coefficients associated with the first linear equations are 1 minus the transpose c, 0, and 0. The coefficients associated with the second linear equations are 0, the matrix A, the identity matrix I, and the vector b. In addition, we also need a column to indicate the basic variables that are selected at each step of the algorithm. In the first stage, the variable s is the basic variable. After writing down the system of linear equations of constraint in a tabular form, we then select what variables are entering variables and what variables are leaving variables. And the selections is based on the criterion that the entering variables will have minimum values minus cjt, and the leaving variables will have positive aij and minimum ratio bi to aij. After determining what variables is the entering variables and what variables is the leaving variable, we then apply the Gaussian elimination to transform the column Xj into a column consisting of only 0 and only 1 at the entry Aij of the matrix A. Moreover, we also need to train the Si in the basic variable column into Xj to finish this step. And we then continue the algorithm until all of the elements in the circle regions are non-negative, because Si's and Xj's are non-negative. So if the coefficients associated with them are non-negative, we then can eliminate their roles in the optimization problem by setting Si a 0, because now Si is a non-basic variable. Now we try to apply the simplex method to solve the earlier example. We aim to maximize the function y, which is equal to 4x1 plus 3x2, where x1 and x2 satisfy the constraints 4x1 plus 2x2 less than or equal to 8, x1 plus x2 less than or equal to 3, x1 and x2 are non-negative. Firstly, we need to transform the general form of the optimization problem into a standard form. Is the following I wrote in the slide. You can see that. Then I write down a tabular form of the system of linear equations of constraints is a table of dimensions 4 by 6. The coefficients with respect to the system of linear equation is the following: 1 minus 4 minus 3 0 0 0 0 4 2 1 0 8 0 1 1 0 1 3. And then we can see that minus 4 is the smallest negative number in the second row of the table, so x1 is chosen to be the entering variable. However, because 4 and 1 are both positive, so both x1 and x2 can be leaving variables. However, in this step, we only select x1 as the leaving variable because the ratio 8 to 4 is the smallest among the ratios 8 to 4 and 3 to 1. Then, by applying the Gaussian elimination, we can transform the column x1 into the column vector 0, 1, 0. And we also change the x1 in the basic variables column into x1 to finish the step. And we continue the algorithm since there is still one negative number minus 1 in the second row of the table. At this time, we had only one option. X2 is the entering variables and S2 is the leaving variables. And by applying the Gaussian elimination again, we can transform the column X2 into the column vector 0, 0, and 1. And we also change the S1 in the basic variable column into X2, and we finish the algorithm with the one optimal solution 1 and 2. So we finish the lecture here, and please find more examples to have a deeper understanding of the simplex method. Thank you for watching and see you in the next video.